Hello, everyone. Thank you for coming to the conference Energy 4.0. It's a pleasure to be here to talk to you. Unfortunately, we can't be in person at the same location, but I hope that the 3D environment gives a little bit more of a feel. I look forward to interacting with you at the end of the talk and throughout the event. So I'll be talking about machine learning in the energy industry today. My name is Patrick Bangert. I'm the Vice President for Artificial Intelligence at Samsung SDS, which is the IT company in Samsung Group, where we deal with all manner of AI. And I'll be exploring how that is incorporated in the energy industry and what the benefits might be. So just a little recap. Artificial intelligence, of course, is a mathematical methods sector, so it needs to be connected to reality, the real world, which is really where the term Internet of Things comes in. This is the sector that really connects the real world to the digital world via sensors and things like that. So there's numerous things that you already have, which would be the machines, the sensors that acquire the data. You have a control system that runs either your upstream or your downstream area. You have an archive of that data. All of that is principally a physical asset. Even the data archive is essentially a physical asset. It's a data center with hard drives and so on. And unless you analyze that data archive, it remains a physical asset. The value that IoT or analysis or machine learning or artificial intelligence, any of these fancy buzzwords can provide you with is actually to optimize that process, to achieve better control, to increase the quality, to stabilize whatever process you're running, perhaps even to document it to a regulator. The primary use case, of course, that everybody has been talking about for years now is maintenance, or rather predictive maintenance, to help you schedule events before a physical failure. And how to connect these worlds that exist and the value that we hope to get from it is really via a database and analytics on that database that will drive the model that will allow you to do all of these things computationally. Now, the word model is, of course, bandied about quite a lot in the discussions around artificial intelligence. So I thought I would say a few words about what this magical model might be. You've met it many times in your education in high school, at university, and so on. This model is not an esoteric concept, but rather it is a formula. Here is an example of a model and a modeling process that human beings have done over history and arrived at a result that we use nowadays. So in the Middle Ages, in the 16th century, Tycho Brahe observed the planets every night through his telescope, and it took him 21 years to establish a table of planetary positions. Later on, John Kepler then used that data to convert it into the three laws that we learn in high school as Kepler's laws, which eventually were transformed by Newton into Newton's laws. And those simply tell you that planets move on ellipses, and there's a certain formula that describes how quickly they do this. And that formula or those laws, that is the model. So in other words, a model is an equation, a mathematical language description of how the real world behaves, and as such is really a summary of empirical data that somebody has collected. In the olden days, here it was a manual collection process where Brahe actually wrote the numbers down in a notebook. Nowadays, it's an automatic data collection process with a sensor and a database. But the idea remains the same. You collect empirical data by some means, then you analyze it to find a pattern that is contained in that data, and you write that pattern down in mathematical language. And that mathematical language, that is the model. Now, the model that a human being produces is generally quite compact, like we see here on the slide. The equation is pretty short. We can write it down on a napkin. If we understand what the letters refer to, then we arrive also at some understanding in our minds on what that might mean or what the implications are of that. And that is, of course, the principal tax that you pay for artificial intelligence. The models that AI produces are in general so complicated, so long, that we can no longer write them down on a napkin and come to a human understanding, but they still work. And that is the primary benefit that we attain from AI. We develop the models very rapidly without having to invest 2 or 3 decades of human expertise into it, but we lose the understanding. And that's, of course, where many of the quibbles that people have in the energy industry and others with this process. So let's look at something that we usually call the digital oil field, which is an example of how this works in practice. So in the energy industry, of course, we deal a lot with the upstream and midstream sector by which we extract our oil or the gas, or in fact any other kind of mining asset from the ground, and then transport it to some sort of a factory where it is refined or made into goods that we can use. These are typically occurring over large geographical areas, many of which are inhospitable or difficult to reach because they might be in a very cold or a very hot or a very underpopulated area. And so usual connectivity is a challenge, getting internet out to these locations. So the first step in the digital oil field or the digital mine is really to digitize this. And the first error that the energy sector makes here is to confuse digitization with the digital transformation. Digitization, all it refers to really is to make available the information gathered at that place digitally in some method that is accessible to people who are not physically resident in that location, right? I hesitate to use the word cloud because it doesn't necessarily have to go via the internet to a server that's accessible to other people outside your organization. It could be a server that you own and run, and that's only accessible to people who work for the same company, and it's a very secured environment. But nonetheless, the data must be available on a central server somewhere where it can be used by people in different locations. So digitization is that process by which you have sensors that produce numbers. Those numbers have to somehow be able to transport themselves to a central location. And so you see on the diagram lots of white lines which indicate either wireless or wired transport lines by which data is collected from various endpoints. Those endpoints could be cameras where the data is an image. It could be the usual sensors where the data is a number, or it eventually becomes a time series, like temperature over time, volume over time, efficiency. It could be human related, like where is the workforce, which is essential for things like sending ambulances out into the field when there is a problem. You need to know who is out in the field, where are they, so that if they are in distress, you can very easily locate and rescue them. So various types of data is collected. That needs to be integrated into a workflow. That data has to be used for some purpose. And so there needs to be a workflow that dictates what happens to that data. On that basis, we can then do the usual artificial intelligence things we talk about. We can forecast maintenance activities, we can optimize processes, and thereby we can track the profitability of all these efforts. Digitization is the entry level, but it is not the destination. Beyond that, we of course have a few differences to what is usually regarded to be IoT. So if you Google IoT, don't believe everything you see at face value. For example, a popular thing to say is that sensors have become very cheap. Well, they have if you're thinking about an RFID chip in a supermarket. But the oil and gas industry, or mining in general for the energy industry, is not that way. We need to deploy sensors in harsh environments, generally outside. Maybe it's very hot or very cold. These sensors need to survive harsh conditions. And so sensors are generally actually quite expensive, thousands of dollars typically, to purchase, install, and connect a single sensor. And so there is an investment associated with digitization. Then typically mines and oil fields are in large areas, remote areas, so that there is a data transmission issue. For example, the oil field in the Kingdom of Bahrain is 10 miles wide by 10 miles high. So you're talking about a Wi-Fi system that has to work over 100 square miles. That again is an investment issue to make sure that the data transmission works out. Inaccessible locations makes for long response times, right? So if something goes wrong, until the maintenance crew gets in a truck and drives out there, some hours will go by. And so the need for prediction forecasting events is quite different from normal IoT, where all you have to do is walk downstairs to the data center. So keeping that in mind, there are a number of requirements to this integrated workflow, which starts with measuring and transmitting that data, then recording and visualizing it to people on a diagram, then having to interpret and diagnose what is wrong, what we're going to do about this. Then you need to actionize and plan. So what exactly are we going to do? Who's going to do it? When are they going to do it? Where are they going to do it? What do they need in order to get it done? And get them out there. And then, of course, track and trace. What has been done? Was it beneficial? Did it achieve its outcome? What can we learn for next time? This entire workflow has to be integrated, digitized in such a way that the handoffs between all of the individual people that are involved here is seamless and quick. So all of that can be done. Within the oil and gas industry specifically, there are many use cases, and I will not read through every single bullet point here, but the point of the slide is to get across that artificial intelligence has been used in a huge variety of different, very specific and targeted use cases to help either make the process safer, more efficient, cheaper, or obtain more revenue from the process, and in such way has been very beneficial to the business. Some of the lessons that we learned is that, for instance, the investment in the sensors is significant. So the entry level financially is unfortunately expensive. But once you've made that investment, the rest of the process is financially very cheap. The investment in software and the investment in analysis is very cheap compared to the investment in physical assets like sensors. You do need people, and you do need to focus on change management, and I'll get back to that in a minute. Some of the effort is invested into integrating all these IT systems. So if you want to do artificial intelligence, don't ignore the pedestrian efforts in actually doing the integration of software and IT systems. You need to put in some effort into all of this. And of course, some effort has to be expended on data science and artificial intelligence, but actually, in terms of the total number of labor hours, the hours that go down for data science and AI are actually in the minority. It's all the other stuff around it that is essential to help that system thrive. So there is more to it than data science. Let's look at what this might be. So generally, you think, I have some domain experts, let me upskill them in data science, or let me hire some data scientists and put them out in the field for a couple of days, they'll figure it out. My personal experience over many projects over the last 20 years has been that these attempts have virtually always ended in failure, because you simply cannot make one expert into an expert about a completely different area in effectively no time at all. Both people, the data scientist on the one hand and the domain expert, whoever that might be, the oil and gas expert, the mining expert, they will have spent years in education in their domain. They will have spent years more gaining experience, hands-on practical experience in their area. They will know about their tools. They will have a network of other people available. They will be able to do certain things in their area. Trying to convert them to be an expert in the other area will require an investment of years, which is not efficient. So one of the fundamental statements that I'd like to impart onto you is that the data scientist and the domain expert cannot be the same person. They necessarily are two people. In real life, they typically are about 10 people, because you need different domain experts and different data scientists. You might need a domain expert for the data historian, for the process control system, for the upstream sector, for this and that type of machinery, so that they together represent the problem or the situation. And the data scientist, you might also need more than one to do, for example, data cleansing and annotation, to do the machine learning, to do the interpretation and communication of the results. So you're looking at a team effort. That's my main statement here. And these two roles need to interact with each other, communicate, so that they learn from each other, and together they're able to both define the problem and solve the problem as a team. Now, what could be the problem? In terms of applying machine learning and artificial intelligence to, to the industry, there are 6 major areas that, in my opinion, cover most of it. One of them is anomaly detection, where all you do is say, this doesn't look normal, and alert that fact to a human expert who will then have to check out the rest. The second is a forecast. You say, tomorrow the situation will be like so-and-so. This is akin to, of course, the weather prediction that we watch on telly every day, but this will be much more detailed in terms of a time series where you might forecast what a well does and so on. Diagnosis is where you say, this is of a certain type, right? This type of data is indicative of a certain problem or non-problem, and then you might want to alert people to that fact. Soft sensor, where you convert a laboratory measurement to a calculation. This has become very well known in recent years, because laboratory measurements, of course, are unsafe. Somebody has to collect the sample. They are expensive, and they are very infrequent. You have to collect the sample, drive it to the lab. They have to make measurements. So you might do that once a day or a couple of times a week. Once you convert that to a calculation, it can be in real time. Advanced process control, of course, has been around for a long time. AI assisted allows that to be nonlinear and therefore a lot more efficient and effective in getting the process controlled. Process optimization is kind of the most advanced stage in all of this, where you actually uplift the efficiency or effectiveness of the process by a full-on digital twin modeling of whatever process you're looking at. So virtually all of the use cases that I've seen in the energy industry fall into one of these 6 buckets. So if you think about those 6 concepts as being the possibilities, and then think about what might be your use case in your plant, taking that template and applying it to your process, you'll most likely be able to hit the right papers. Obviously, at some point, the business is going to have to come into this, and we'll need to define a larger ecosystem that consists not only of data and technology, but also the processes, the experience of the people, having a look at the industry, and of course, the business model to make sure that whatever it is that you are doing is going to be not just interesting, but profitable at the end of the day. So that needs to be taken into account, which will involve a large number of more people into the whole team, which makes it necessary to look at change management. This is a popular process display of change management where people initially are skeptical whether or not this will impact them individually with their own private lives or career lives in a good or bad way. And typically people will look at the disadvantages first, and it is then up to leadership to help people interpret this correctly for themselves and put themselves into context, and then actually like this process and see the change as somehow beneficial to them, right? So not only should this whole digitization, digital transformation, AI process be beneficial for the company and the physical assets, but it needs to be beneficial to the human people involved as well, and that needs to be communicated. And that in practice, again, in my personal experience, as well as many others, takes effort and time and investment into getting this done properly. I want to tell you about a few case studies where this has yielded some good benefits. So here, first of all, is a portrayal of process optimization, where here you're looking at 2 set points in the horizontal axis and the axis into the slide. And the vertical axis here is the result of changing those 2 set points, where we like the yield to be higher. So the mountain tops are good points and the valley bottoms are bad points in terms of yield. You can see that if we start at the point on the left-hand side and provide the identical conditions to the human, who is going to choose the gray path, and the AI is just going to choose the green path, they end up at different points, where the optimal point, according to AI, is in fact 5% higher in yield than the human-chosen gray path. Not only that, during the transition, the yield was higher along the green path. So AI in this particular case has yielded a 5% greater output of the process than the human-guided process. And so the benefits here are real. And of course, for real plants, 5% translates to rather a lot of money generally. And so the profitability of such becomes immediate and very transparent. You can do things like load balancing between many wells connected to a single offshore platform that drove the yield up 7%. You can model the output of NOx and SOx measurements in the field very accurately, which allows you to get rid of the actual sensor array, which is expensive to buy and expensive to maintain. And there are, in some places, like in California, in the United States, there are regulatory fines when these sensors fail. So again, the business context here is immediate, and the mathematics is actually quite ready and easy to deploy. In many cases, it is vibration that is the best indicator of what's actually wrong with a piece of equipment, because there you don't just get a number, you get a whole spectrum of values, and then there's a fingerprint of a particular issue. We're used to seeing chemical emissions spectra that tell you what piece of material, what chemical element is in a piece of material. In this case, you're looking at vibration spectra going across in the horizontal line, and vertical, they are stacked on top of each other over time. In this diagram, you're looking at 6 months worth of vibration spectra stacked on top of each other. Blue here is very low vibration, green is medium vibration, black is very high vibration, so you see the amplitude in color. Clearly, there was some state of process that is more or less constant. At some point, you see it getting blacker and blacker before it hits a period where there's an obvious outage. The entire section was offline, and then post that again, you have a continuation of the same thick black lines here. So obviously a problem developed weeks prior to the outage, which was perfectly visible in a diagram like this. And artificial intelligence can quickly catch on to this. And it can then do two things. It can forecast when the outage is going to happen. And at the same time, it can tell you this is the vibration fingerprint of a certain kind of problem. So I can put a name to the madness and schedule a maintenance activity that can solve the problem. So diagnostics is possible by AI, and vibration signals are perfect for this. So just to sum up, artificial intelligence has many applications in the energy industry, in forecasting things, in diagnosing things, in optimizing things. The use cases abound in the industry. And if you want to learn more, I recently published a couple of books on the topic. There's machine learning in the oil and gas industry and machine learning in the power generation industry that are available from Elsevier if you want to read either some more about how artificial intelligence is actually deployed, what it is, how it's done, as well as reading about numerous case studies written by colleagues of mine from real operating companies, real practitioners in the field that have deployed these methods. That will give you much more information. You're also perfectly welcome to contact me directly at my email, via LinkedIn, or on my YouTube channel, where I present situations like this. So thank you very much for your attention, and I hope to speak with you soon. Bye-bye.